Welcome to the Deep Dive, where we take a stack of information and extract the most important nuggets to get you well informed fast. Today, we're diving deep into something really critical for anyone in modern cloud environments: optimizing Istio telemetry for Prometheus cardinality reduction, especially if you're, sharpening your skills for that next big DevOps or cloud engineering interview. Think of this as a focused session. We want to give you both the quick answers and the detailed understanding you'd need to really discuss this confidently. We've pulled insights from some pretty expert level documentation on this exact challenge.
That's absolutely right. Our mission today is to unpack why high cardinality isn't just like a small issue, but often a full-blown crisis in Istio deployments. And then we'll walk you through the practical, effective strategies to bring those metric series counts down. We're talking potentially millions down to manageable thousands. We'll look at in-mesh optimizations, post-scrape techniques, and even some advanced strategies you see in really large-scale systems. By the end, you should have a solid grasp of the what, and crucially, the why it matters, both for your systems and for those interview chats.
Okay, great. Let's unpack this problem first then, because for anyone prepping for a senior DevOps or cloud engineering role, this often comes up, right? So here's the question we often hear. What are the core challenges of high cardinality in Istio telemetry, and how does it actually manifest in a Prometheus environment? I mean, for someone who hasn't maybe lived through the pain, what does that feel like on the ground?
Yeah, that's a good way to frame it. Okay, the quick summary is high cardinality means way too many unique time series, just too much unique data. And this can completely overwhelm your Prometheus setup. What does it feel like? Massive memory consumption is the big one. Queries that take forever. And storage costs just spiraling upwards, the root cause. It's Istio's default metrics. They're incredibly detailed, which is good in theory, but every unique combination of labels creates a whole new series. So the goal really is just to slash that number of series for operational efficiency and, frankly, for sanity.
So it's definitely not just a theoretical problem. It bites hard in the real world.
Oh, absolutely. This cardinality crisis, as some call it, is genuinely one of the biggest operational headaches in modern service mesh deployments. Seriously. Let me throw some numbers at you to make it real. When you're dealing with, say, 10 million time series.
Which isn't uncommon in big setups, right?
Not at all. So 10 million series often means memory usage easily topping 40 gigabytes per Prometheus instance, just for Prometheus. And your queries. Things that should be quick, maybe a second or two. They start taking tens of seconds. Imagine trying to troubleshoot an outage like that. It's a nightmare.
Yeah, that's painful.
And the storage needs just grow exponentially. It costs more, needs more management. It just becomes this constant firefighting situation.
That sounds exhausting. And expensive, both in resources and engineer time just keeping the lights on.
Exactly. It's the human cost, too.
Yeah.
So the root cause, as I mentioned, is Istio's default telemetry. It's very comprehensive. It generates metrics with lots of labels. Things like source app, destination service, source version, destination version response code, request protocol. I mean, the list goes on. And here's the kicker. Each unique combination of these labels creates a new time series.
So even one different version number or a different response code, boom, new series.
Precisely. Think about deploying a new version, or just different HTTP status codes for the same service path. Each one multiplies the possibilities. Yeah. It's like, imagine trying to count people in a huge stadium, but instead of counting sections, you're forced to count every single person individually by their seat number. That's high cardinality.
Okay, that makes sense.
In large deployments, with lots of services, frequent updates, lots of traffic, this just inevitably leads to a cardinality explosion. Makes Prometheus really tough to manage.
Right. So if you're seeing those symptoms, high memory, slow queries, what are the absolute key takeaways about why this is happening?
Okay, three main things to hammer home. One, high cardinality directly tanks Prometheus performance memory, queries, storage, all suffer. Two, Istio's rich default telemetry, with all those detailed labels, is the main driver. It's a feature, but with a big side effect. And three, managing this isn't optional. It's crucial for operational stability and cost efficiency in any serious service mesh setup. It's foundational for healthy monitoring.
Okay, crystal clear on the problem. It's a beast. So knowing the problem is half the battle, as they say. Let's talk solutions. What's the first, most impactful step someone should take? This is where you show that practical Istio knowledge, right? So the question becomes, what are the primary techniques to reduce Prometheus cardinality for Istio telemetry, starting with in-mesh optimization?
Right. The first place to look is the Istio telemetry API, specifically a feature called tag overrides. This lets you remove those high cardinality labels right at the source. in the Envoy proxy before they're even scraped. Think of it as pre-filtering.
Ah, cutting it off at the pass.
Exactly. Then your second major tool is Prometheus's own metric relabel configs. This happens after scraping but before storage. So you get another chance to filter or transform metrics. Using these two together gives you a really significant initial reduction.
Filtering before it even gets into Prometheus sounds super efficient. Less data to process, less data to store.
Totally. Let's dive into that first one. The Istio telemetry API. This is really the modern, declarative way to handle Istio metrics customization. It replaces older methods like config override, which could be, let's say, a bit clunky and harder to manage at scale. The real power here lies in tag overrides. It gives you fine-grained control over which dimensions, which labels get attached to your metrics by Envoy.
So you can just tell it, don't even bother generating this label.
Precisely. You target labels that are known cardinality offenders, labels that often don't add much value for your main SLIs. Things like requested unique per request, useless for aggregation, or destination principal, source principal, maybe connection security policy, often static or not needed for performance monitoring. Even things like corrupt response to status, or source version and destination version if you have tons of versions flying around, or request protocol.
Those version labels seem like a prime candidate for explosion in CI/CD environments.
Definitely. So you use the operation. Remove directive in your telemetry resource for these labels. The beauty is it happens in the Envoy proxy. So you reduce memory use in the sidecar and you cut down network traffic because fewer labels are sent to Prometheus. Just doing this, you can often see an immediate 60–70% drop in cardinality. It's a huge win right off the bat.
Wow, 60–70% just from that first step. That's massive.
It really is. It sets a much better baseline.
Okay, so you've done that initial stripping in Envoy. What about that second line of defense you mentioned before data hits the Prometheus database?
Right, that's where Prometheus relabel configurations come in, the metric relabel configs. These rules run after Prometheus scrapes the metrics from Envoy, but before they get written to the time series database, TSDB.
So it's like a final cleanup crew.
Exactly. It's your last chance to modify or drop labels or even drop entire metrics before they consume storage. And you can get quite sophisticated here. You can do things like global label dropping using regular expressions. Maybe you misrequested in the telemetry API, or you want to ensure a destination principal is gone from everything relevant. You can enforce that here.
Okay.
But where it gets really powerful is conditional label dropping for specific metrics. Take histograms, like Istio request duration milliseconds bucket. For latency calculations, you need the buckets, but do you really need the response flags or even response code attached to every single bucket? Probably not.
Right. The latency distribution itself is the key thing there.
Exactly. So you can use source labels and regex in your relabel config to target only that bucket metric and drop response flags and response code from it. This can slash the cardinality of your histogram metrics by 80–90%, sometimes more, while keeping your ability to calculate P95, P99 latency perfectly intact.
That sounds incredibly useful, being surgical like that.
It is. You can also use relabeling for metric filtering, basically, and a lie list. You can say, I only want to keep Istio request total, Istio request duration milliseconds, and its variants like sum, count, bucket, and maybe the Istio P metrics. Everything else, drop it.
So you're actively choosing what to store, not just passively accepting everything Istio throws out.
Precisely. Be intentional about what you monitor and store.
Okay, so if someone's taking notes on this section, what are the big takeaways for getting started with reduction?
All right, key points. First, the Istio telemetry API, using tag overrides, is your best first step. Remove labels at the source. In Envoy, it's the most efficient. Second, Prometheus metric relabel configs act as a powerful second layer. Filter and transform after scraping before storing. Third, focus your initial efforts on high cardinality labels, IDEs, principals, maybe detailed versions or protocols. Quickest wins there. And fourth, leverage conditional relabeling. It lets you optimize specific metrics, especially histograms, in a very fine-grained way. Be surgical.
That's a fantastic breakdown of the initial cleanup. But okay, you've done that. You've maybe gone from millions to, say, hundreds of thousands of series, still potentially a lot for massive environments, right? How do you scale this further? This feels like where we get into the really big picture thinking. So, the next question. Beyond initial label removal, how can aggregation strategies like recording rules and federation further optimize cardinality for large-scale Istio deployments?
Ah, yes. Now we're talking about the heavy hitters for large scale. You've got two main tools here, recording rules and federation. In a nutshell, recording rules pre-aggregate your high cardinality data into much smaller, summarized metrics on a regular schedule. Think pre-calculation. Then, Federation lets your central or global Prometheus instances collect only these pre-aggregated metrics from your local Prometheus instances. This distributes the load and helps with long-term storage. Honestly, these are essential techniques if you're managing millions upon millions of series and need that global view.
Okay, recording rules first. You called them most powerful earlier. Why is that?
Because they fundamentally change the nature of the data you store long-term. Recording rules let you define expressions that Prometheus calculates at regular intervals, say every 30 seconds or every minute. The result of that calculation is then stored as a new time series, usually with far fewer labels.
So instead of storing raw data points, you're storing calculated summaries.
Exactly. The impact is transformative. You can take literally millions of raw, high-cardinality series and condense them down into maybe just thousands of aggregated metrics. This dramatically cuts down what Prometheus needs to store and, crucially, what it needs to scan during queries. Performance skyrockets.
I can see how that would help. Do you have an example?
Sure. Think about request rates. You might have Istio requests total with labels like source app, destination service, destination version, instance pod, response code, etc. Millions of series. You could create a recording rule like, say, service.istio request rate 5 meters, some rate, Istio request total 5 meters by source back destination service name, destination service namespace response code.
Okay, so you're summing the rate over 5 minutes and only keeping a few key labels.
Right. You're aggregating away the instance details, the pod details, maybe the specific version. This single rule could easily give you 1,000-to-1 reduction in series count for that metric.
1,000 to 1, wow.
Yeah, and you can build hierarchies. From that service level rule, you could create another rule for namespace level aggregation. Namespace.istio request rate 5 meter equals sum service.istio request rate 5 meter by destination service namespace response code. That might be another 100-to-1 reduction. You could do similar things for latency, like calculating P99 latency, but only keeping service or namespace level labels.
So you end up with layers of aggregation.
Exactly. A common pattern in big enterprises is raw pod level metrics, maybe millions of series. Aggregated service level metrics, tens of thousands.
Right.
Aggregated namespace level, hundreds, and maybe even cluster level, tens. Different teams query different levels.
That makes sense. Different levels of detail needed. Now, what about federation? How does that fit in?
Federation is primarily for scaling out your Prometheus setup, especially when you have multiple clusters, regions, or just very large single clusters.
So distributing the load.
Exactly. The idea is you have local Prometheus instances in each cluster or region. These scrape the raw high cardinality, but hopefully already somewhat reduced by telemetry API and relabeling metrics locally. They also run the recording rules to generate the aggregated metrics. Then you have one or more global Prometheus instances whose only job is to scrape just the aggregated metrics from the local instances.
Ah, so the global one doesn't see the raw noise.
Precisely. You configure the global Prometheus' scrape configs using the match parameter. You tell it something like match name service.namespace.
So only grab metrics that match your aggregated naming convention.
Yes. Only pull the results of the recording rules. The benefit: you get a global, consolidated view of your key indicators across your entire estate without the global instance needing the massive resources to handle all the raw data. Plus, you still have the local instances for deep dive troubleshooting when needed. And you can have different retention policies, keep detailed local data for maybe 7 or 15 days, but keep the aggregated global data for months or even years.
That sounds like a really robust architecture for large scale. Okay, takeaways for this section, for someone building that big system.
Okay, key things for aggregation and scaling. 1. Recording rules are incredibly potent for pre-aggregating metrics, massively cutting series counts by summarizing hierarchically. 2. Think in layers. Pod-service-namespace-cluster. This tiered approach gives you granularity control and progressive reduction. 3. Prometheus Federation is your friend for horizontal scaling and distributed observability. But crucially, only federate the aggregated data from local instances. And 4. These strategies combined are really essential for managing observability at enterprise scale. They let you maintain that crucial global visibility without drowning in local detail.
Fantastic. So we've got the initial cleanup, the powerful aggregation, we have the techniques. But let's talk about actually doing this, the nuts and bolts, the process, the potential traps. This feels like where an interviewer really probes if you've done this for real, understand the practical side. So the question is, what practical implementation phases and critical considerations, including potential trade-offs, should one be aware of when embarking on a cardinality reduction project for Istio?
Right, the how-to and the what to watch out for. Okay, quick summary. It's usually a phased process. You analyze labels, apply metric-specific tweaks, roll out recording rules, and then you must validate continuously. The big wins are huge performance improvements, memory query speed. But the critical thing to remember is the trade-offs. You are giving up some granularity, which can impact debugging, security views, and version tracking. You need to be okay with that.
Okay, let's break down that implementation strategy. Where do you even begin? What's phase one?
Phase 1, label analysis and removal. You absolutely have to start by understanding where your cardinality is coming from. Prometheus has an API endpoint, a PEV1 label name values. It's super useful here. You can query it to see which label names have the most unique values and which label combinations are exploding.
So data-driven decisions, not just guessing.
Yes, exactly. Find your biggest offenders. As we discussed, usual suspects are requested, no aggregation value. Destination principal, source principal, often not needed for SLIs. Connection security policy, often static. And those source version, destination version labels that cause version explosion. Target these first with the Istio telemetry API. Tag overrides. Get those quick wins.
Okay, analyze and remove the low-hanging fruit. What's next?
Phase 2, metric-specific optimizations. Realize that one size doesn't fit all. Different Istio metrics need different treatment, mostly using Prometheus relabeling now. For Istio requests total, you probably want to keep response code for error rates, but maybe drop response flags. For the Istio request duration milliseconds bucket histogram, as we said, you can often drop both response code and response flags because you just care about the latency distribution shape. For byte counts like Istio request bytes, Istio response bytes, you're looking at throughput patterns, so drop response-specific labels there too. Always ask, what are the absolute minimum labels I need to calculate my core SLIs for this specific metric?
Be selective. Got it. Then the recording rules.
Phase 3, recording rules implementation. Now you build those aggregation layers we talked about. Podbuff service, maybe 1000.1 reduction. Service namespace, 100.1. Namespace serverland cluster, 10.1. The absolutely critical consideration here, ensure your recording rules preserve the dimensions needed for your key SLIs. Your golden signals latency, traffic, errors, saturation must still be calculable from the aggregated metrics. Define the rules to eliminate noise but keep the signal.
So define your SLIs first, then build rules to support them.
Precisely. Don't aggregate away something you actually need.
And the final phase.
Phase 4. Validation and monitoring. This isn't a one-off project. Cardinality can creep back up as your system evolves. New services, new label.
Monitoring the monitoring system?
You got it. You need to continuously monitor key indicators of your monitoring health. Watch Prometheus head series or similar metrics for overall cardinality in Prometheus. Keep an eye on Prometheus rule group last duration seconds, and maybe calculate recording rule efficiency to make sure your rules are running well and actually reducing data as expected. Catch cardinality regressions early before they become another crisis.
That's a solid roadmap. Now, the reality check. Production considerations, the gotchas. What are the big ones people hit?
Okay, let's talk impact first, the positive impact. Memory and CPU improvements are often dramatic. We've seen real-world cases go from, say, 40 gigabits of Prometheus memory usage down to 8 GB. That's an 80% drop.
Huge.
Query latency. From a painful 30 seconds for a dashboard panel down to 2 seconds, a 93% improvement. Makes dashboards actually usable again. Ingestion rates dropping from 800 milliVs to 150 milliVs, 81% less load on Prometheus and storage. These numbers are typical when you do this right. It buys back so much overhead.
Okay, so the payoff is definitely there. What about the migration hurdles?
Compatibility and migration concerns are real, especially if you're moving from older istiometric config override to the telemetry API. You must disable the old stuff they can conflict. Crucially, test your Grafana dashboards or other consumers before you roll this out widely. Removing labels will break dashboards that rely on them.
The dreaded broken dashboard.
Yeah. So test, test, test. And consider a gradual rollout. Use namespace-specific telemetry resources first. Apply changes to a small set of services, validate, then expand. Don't big bang it if you could avoid it.
Wise advice. And finally, the trade-offs. You mentioned them earlier. Let's be explicit.
We have to be honest about the observability trade-offs. You are choosing performance and scalability over ultimate granularity. Removing requested, for example. It's great for cardinality, but yes, it breaks the direct link between a specific metric data point and a distributed trace in some tooling.
So if I remove requested, how do I debug distributed traces then? What's the alternative?
Great question. You lean more heavily on your dedicated tracing system, Jaeger, Tempo, Zipkin, whatever you use. You correlate traces using trace IDs within the tracing system itself or via logs. You accept that Prometheus metrics are now primarily for aggregated performance monitoring, not per request debugging.
Okay, so use the right tool for the job. Metrics for aggregates, traces for specifics.
Exactly. Similarly, removing source principal or destination principal means you lose some auth context in Prometheus. You'd rely on audit logs or identity system logs for that detailed security investigation. And removing source version or destination version makes fine-grained canary analysis based purely on those metric labels harder. You might need to rely more on deployment tooling data or application-level version reporting. You need to understand what you're giving up and ensure you have alternative ways to get that information if needed.
That's a really important clarification. It's not magic, it's engineering trade-offs.
Absolutely. And just briefly, some advanced techniques are emerging too. Things like dynamic label management, maybe only keeping certain labels during incidents. Tools like Victoria Metrics have some features for this. Even ML-assisted cardinality prediction is being explored. And thinking about this across the whole stack application, infra storage is becoming more common.
Fascinating. So, boiling it all down, what are the core principles for doing this successfully in the real world?
Okay, 4 key things. 1, use a phased approach, analyze, optimize metrics, implement rules, validate, be systematic. 2, expect dramatic resource improvements, memory, CPU, query speed, but quantify them to justify the effort. 3, plan your migration carefully. Test compatibility, roll out gradually, avoid surprises. And 4, critically, understand and communicate the observability trade-offs. Know what granularity you're losing and why, especially around debugging and security. Manage expectations.
Wow. Okay, that was genuinely a deep dive. We've covered the crisis, the multi-layered solutions from the telemetry API and relabeling right through to recording rules and federation, and the practical steps and trade-offs.
Exactly. And achieving that goal, like a 95% reduction
Correct.
in Istio cardinality, going from 10 million series down to maybe 500,000, it sounds ambitious, but it's totally achievable. It really boils down to systematically applying these different techniques together. There's no single silver bullet. It's the combination that works.
So for you listening, hopefully this gives you a much deeper, much more practical handle on this, whether you're facing this in your own environment or preparing for those tough interview questions on observability at scale.
Yeah, the ultimate goal is always that balance, right? Maintain visibility into your essential SLIs, your latency, traffic, errors, saturation. Keep those golden signals clear. But diligently hunt down and eliminate the metric noise, the excessive detail that just degrades performance and costs money. It's about finding that sweet spot. That's all for this topic. Stay tuned for the next DevOps Cloud interview question.